Hello and welcome back to Calculus 1. This is the first part of 4.5, second one I guess next week. So we're only going to talk about linear approximation, i.e. tangent lines. And the purpose of this is to develop a method of computing, approximating values of things that we generally use calculator for. My question is, how much is the square root of 10? How much is ln of 3? Right? How much is sine of 27 degrees? Right? These are the things that I want to compute without use of a calculator. Right? Now, I know we have calculators and we can use them and so and so. So let's take a look at, let's say, how about the square root of 3? Let's start there. So, okay, I have a square root of 3. I know the graph of square root, so I just want to set up, what's happening here. And I know that this is the square root x function. And as I feed in the x values, the y values pop up on the other side. So if I feed in 1, I get 1 back. Let's say 2, 3, 4. If I feed 4, 2 comes back. But I'm actually interested at value 3. I want to know, right, if x is equal to 3, how much is the square root of 3? Now look at this awesome, awesome, awesome thing. I don't know how much square root of 3 is, but I know how much the nearby square root of 4 is. Nearby. I'm not talking about square root of 100. That's far away. But square root of 4 is close to square root of 3. Look at this. If I find the tangent line at 4, which is easy for me to compute without calculator, look what happens. The tangent line is very close at 3 as well. See that? So now I'm going to find the tangent line using 4, and that tangent line is going to be some kind of mx plus b, and I'm going to plug 3 for that x. The value that I compute in a tangent line and the value for square root of 3 are not the same, but they will be very close. And that's how we approximate. So let's do this. Procedure for tangent line. I know that my function f of x is root x because I'm trying to compute root 3. So common sense, the function is root x. I know I need the derivative for tangent line, which is 1 over 2 root x. And to calculate the slope, I will compute that at 4, because that's the one that I can compute. So it becomes 1/4. Now, I'm using a point, so what's f of 4? F of 4 is the square root of 4, which is 2. So I have a point 4, 2, and I have a slope of 1/4. Y equal mx plus b. Y is 2. M is 1/4. X is 4. Plus, it's just a standard procedure. So b is 1. So tangent line is y equals 1/4 x plus 1. Tangent line at x equals 4. I'll put in parentheses, close to 3. You know what that means. I also can take square root of 9. I can take a square root of 1, but 1 is 2 units away from 3, and 4 is 1 unit away from 3, right? So 4 is closer. You take the closest possible location that you can, that it's easy to compute without a calculator. And now what do you do? You claim that the square root of 3 is approximately 1/4, you plug 3 in, plus 1. That's 3/4 plus 1. That's 7/4, 1.75. So you are claiming that the square root of 3 is approximately 1.75. Guys, you did this with a stick in a sand. There was no calculator involved, nothing, right? That was it. What does the calculator say for the square root of 3? Calculator says 1.732. Yeah, big deal. You are 2 cents off. What can you buy for 2 cents? Just people's opinion. That's it. There's nothing else, right? And here's my 2 cents. Keep your 2 cents. That's exactly how much it's worth. All right? We just calculated root 3 by hand. How about ln of 3? Can we do that one? It's going to be the same stuff. Your function f of x is ln x. The derivative is 1 over x. And we are going to compute this at the value x equals e. Because e is easy to compute with ln's, right? It's close by. And, yeah, right? So what's the derivative computed at e, which is giving me a slope? It's going to be 1 over e. And the y value is ln e, which is 1. So now I have a point, e1, and the slope of 1 over e. Y equal mx plus b. Y is 1. M is 1 over e. X is e plus b. 1 equals 1 plus b, because e is cancelled, and b is 0. Cool, right? Tangent line is y equals 1 over ex. That's that. So now we claim that ln 3 is approximately equal to computing 1 over e times 3. That's like 3 over e. Well, that's approximately 3 over 2.7, right? It's about 2.7 for e. Memorize that. You memorize pi, 3.14. So don't discriminate. Be nice once in your lifetime. So now, times 10, I get 30 over 27. Cancel by 3. You get 10 over 9. That's 1.11111 going forever. So my claim is that ln 3 is about 1.111 going forever. Calculator, which is also approximation because I'm not going to copy infinity of decimals, gives me ln 3 at 1.0986. 0.99. Hey, it's 2 cents again. You see, this is the way they came up with all of those log tables and things, right? Those tables were not communicated on some mountain to illiterate peasant, right? Here's the book of log tables. No. They sat down, right, and computed. Generally, captains of ships, you know, if you embark on a journey across the ocean, then you're going to be there, you know, for 2 months. Like you have three things to do, like navigation, execution, and this. It's like nothing else. Like, what else you have as a capital tree? So, all right, ln of 3 is done. ln of 3.1. Done. Okay, ln of 3.2. Done. ln of 3.3. Right? This is this, right? So now, all I'm going to do is I'm going to compress this procedure of looking for a tangent line across the page into a single equation, right? Everything is now going to be compressed into the formula, linearization, which is tangent line in disguise. So, tangent line. And the formula says like this. L of x, that's instead of y. L of x is f of a plus f prime of a times x minus a. So this is a single formula for the entire tangent line. So if you want me to linearize anything, I just plug everything in this formula. So example for that, and we're done. Linearize f of x equals to x squared plus 2x minus 1 at x equals to 4. Now, this 4 is your a. That's what it is. So what do? I just plug everything in here. L of x is f computed at a, which is 4 squared plus 2 times 4 minus 1, plus the derivative computed at a, well, that's 2 times 4 plus 2 times x minus 4. And I'm going to actually just write what's what. So this over here is your f of a, so f of 4. This over here is your f prime of 4, that's the slope. And this is your x minus a. So all it is. You compute the entire tangent line in one line. That's 16 plus 8 minus 1 plus 10 times x minus 4. And you just need to clean this up. 16 plus 8, 24, 23 plus 10x minus 40. L of x equal to 10x minus 17. There you go. So now if I needed to compute, right, something that is close to 4, it would be much better to compute it here than computing in the original problem. Because you see that, you know, so part B, find f of 4.3. Well, that will be L of 4.3, which is 10 times 4.3 minus 17. 43 minus 17 is equal to, very good, right? So we are claiming that f of 4.3 is approximately equal to L of 4.3, which is 26. Now if you want to check, compute f at 4.3. That's going to be 4.3 squared plus 2 times 4.3 minus 1. Wow, we're actually gonna go before time? Impressed. Maybe I can squeeze in another example. Everyone's like, no! We listened about first and second derivative test for 2.5 hours. I'm done. So 4.3 squared plus 8.6 when you double that, minus 1. 26.09 is the exact value, no extra decimals. So our cheap, easy, and fast calculation gives us 26, and this gives us 26.09. 9 cents off. Yeah, big deal, all right? So obviously, it will be a big deal if you're working on particle physics, but it's not a big deal if you're building something, because good luck finding any right angles in anything that we built after the pyramids. So, like, that's it. The building precising things ends there. All right, that's that for today. Bye.